All right, so it's time for another installment of Mr. Riley's YouTube channel here. We're moving on with our unit. I plan on having your quizzes graded by Monday, get those back to you, and then during our Zoom meetings, I'll talk about some misconceptions from the quizzes, and then also show you some helpful hints for this unit as well. So we're going to continue talking about trig ratios. We're going to learn 3 new ones today. So you've learned about sine, cosine, and tangent in the past. Today you're going to learn 3 new ones that are also triangle ratios. But the other thing we're going to introduce is we're going to introduce a new unit or a new measurement for rotations. Okay, so you've learned in the past everything's been in degrees, and degrees is a rotational measurement. So it's telling you how much you've rotated. Okay, so if I draw an angle on the XY plane, okay, the reason we have to draw that arrow is because it tells you how much you've rotated. Okay, so this is a rotational measurement. How far did we rotate? Spin this thing, this initial side to the terminal side to get there. And this is probably like, what, 60 degrees. Okay, so that's what degrees are. Okay, now, I always find it interesting that we learn degrees first because they're very arbitrary. Okay, the scale that we use for degrees was just set by someone in the past, and it's just been what we stuck with. In fact, if you think about it, okay, a full trip around, full rotation is 360 degrees. Okay, well, why is 360 degrees a full circle? Well, it has to do with how calendars were planned and the idea that a full trip around the sun is 360 days. So that's why they set it as 360 degrees, not because there's a mathematical reason that a full circle is 360 degrees. That's just what was set as the standard. But anyways, we're going to talk about something that's different called a radian measurement. Okay, and what a radian measurement is it's a distance that is traveled around the edge of a circle while rotating. So the reason that I like radians much better is because it's a distance, it's measurable. Okay, so we rotate a certain degree and we measure the distance that we've traveled. So here's an example here. Okay, so let's say we rotated theta. Remember, theta is our variable we use for degrees for rotation. So we rotate this much, so we rotate from here to here. Okay, if this is the radius, remember radius is the distance from the center of the circle to the outside of the circle. Okay, let's say that's radius r, 1 radian would mean that we traveled 1 radius distance around the circle. Okay, so let's say I drew a circle that had 3-inch, let's say I drew a circle, and let's say my radius is 3. Okay, if I rotate a distance around, so if I rotate to here, okay, and I rotated 3 units as well, 3, let's say this is 3 millimeters, okay, that means that I traveled 1 radian, okay, so radian is just how many radius distance did I travel around the circle. So it depends on the circle. You know, if a circle has a large radius, traveling 1 radian is a very large distance. If it's a smaller circle with a smaller radius, traveling 1 radian is going to be a smaller distance. Okay, so it's all dependent on the circle that you're traveling in. But what we're gonna primarily focus on is how to convert between radians and degrees, because it is a proportion that we can calculate. Okay, and here's the proportion that they use. Well, let's say that we want to travel all the way around the circle. Okay, well, what is the distance you travel all the way around the circle? Well, circumference is equal to 2 pi r. Okay, so what they did is they set the radius as a unit, so they use that as the circumference just being 2 pi. Okay, so they use this as 1 rotation is 2 pi radians. Okay, well, how many degrees is that? Well, that's 360 degrees. Okay, so 1 rotation in radians is 2 pi. 1 rotation in degrees is 360. Okay. To make our conversions easier, instead of dealing with in terms of 2 pi, what's easier is dealing with in terms of 1 pi, because it makes our conversion a lot easier. Okay, so if 2 pi is 360 degrees, how many degrees would 1 pi be? Well, what's the conversion here? What's the relationship between 2 pi's and 1 pi? Well, it's now half a rotation. So how many degrees would half a rotation be? 180 degrees. Okay, so it's a simple conversion using the idea that if we go all the way around the circle, it's 2 pi distance, by whatever the radius is. But if I go half the circle, it's 1 pi distance. So if I want to convert from degrees to radians, okay, what I do is I multiply my degrees by pi. Okay, that's that half rotation. And then divide it by the equivalent of 1 pi, which is 180 degrees. Okay, so we take our degrees, multiply by pi, and divide it by 180. So the important thing about radians, though, is that everything's going to be in terms of pi, because we're talking about circles. So if we're talking about pi a lot, we don't want to calculate pi out and have a decimal answer. You're always going to leave your answers in terms of pi, because it'll make more sense when we talk about fractions of pi. So that's the conversion from degrees to radians. We take the degrees, multiply by pi, and divide by 180. So really, the only thing that we really care about here is, since we're going to leave our answers in terms of pi, is we care about finding out what fraction of 180 is our rotation. Did we travel half of 180? Did we travel 3/4 of 180? Okay, so what we're really figuring out is what's the relationship, what's the fraction of how many degrees we travel in comparison to 180. All right, going the other way, okay, what we do is we multiply by 180 and divide by pi. So it's the exact opposite. And you'll see why dividing by pi is going to help us out with simplifying, okay? All right, so divide by 180 to go degrees to radians, multiply by 180 to go radians to degrees, okay? All right, so let's practice here. I'll do the 80 degrees here. So we're going to multiply by pi and divide it by 180. So what we end up with is 80 degrees pi over 180. Okay, now, a lot of us are better at simplifying fractions, but the expectation is that we do write radians in a simplified fraction. Okay, so we got to simplify 80 over 180. Now, I know back when we were in class, we knew how to reduce fractions on our calculator by using the fraction button. We can do 80 over 180, and it would give us the fractional answer. Okay, so we know that we've traveled 4/9 of a pi. Okay, and that's what that's telling us. Now, we don't have the yellow calculators at home anymore, so you can, on Scientific Desmos, that I showed you that website, you can actually use the fractional button, and it'll give you a decimal answer, but right next to your answer is a fraction button that'll change your answer into a fraction, which will help you with these conversions. Okay, so let me show you going the other way, and then I'm gonna have you practice the other two. Okay, so let's multiply this by 180 and divide it by pi. Now, here's why dividing by pi is nice here. If we have a pi on the top of the fraction, the pi on the bottom of the fraction, what's gonna happen to my pi's? They cancel out, okay? So 4 times 180, if I do 4 times 180, I end up with 720 degrees, because we now converted from a radian, which is in terms of pi, to a degree, which is a rotation, okay? So the important thing to know here is your radians will always be in terms of pi, and your degrees will always be labeled with a degree symbol, okay? So now's a good time to pause the video, and I want you to practice converting this into radians and this into degrees. So pause your video and convert those two and see what you get. All right, so to calculate this, we're going degrees to radians, so we multiply by pi, divide by 180. So we end up with negative 36 pi over 180. And then we were going to want to reduce this fraction. Okay. You can reduce it by, if you have a calculator, some of you have calculators at home that help you out with that. I'm really not, the standard isn't that you can reduce fractions. That's an elementary school expectation. I more care that you can convert it into, you can know how to convert is what I care more about. So if you use your calculator, you use scientific Desmos, we find out that this is negative 1/5 pi radians. Okay, well, just like degrees, what does it mean that if you get a negative radian? Well, it just tells you rotated in an opposite direction. So instead of rotating upward, we rotated downward. Okay. All right, 5 pi over 6. So we're going to multiply by 180 and divide by pi. Okay. Nice thing is pi's cancel out. Okay, so we have 5 times 180 divided by 6. So 5 times 180 divided by 6, and we end up with 150 degrees. Make sure you write that degree symbol if we're talking about degrees. Okay, so that's how you convert between degrees and radians. And about, I would say, a little less than half of your homework is just you practicing these conversions. Okay, so make sure that we're good on that. If you're getting stuck, just let me know. All right. So what we're going to do is we're going to take a little journey and we're going to talk about some special sine and cosine relationships. Now, this is something that's not necessarily going to be on your next assessment this week, but it's something that we're going to use a lot moving forward, so it's important that we talk about it. And as you can see, if you're looking on at your notes at home, my printer is not doing so well, so it's not printing pictures as well as it has in the past. So I have to redraw some pictures here. So we have our y-axis and our x-axis. Okay, and then I'm going to label this triangle. I'm going to label this side as 1/2, and this side is √3 over 2. And I'm going to leave this as just theta. And we're going to study this relationship. Okay, so remember, if you have this is your angle theta. Okay, remember we call this the opposite side. Okay, and then we call this one next to it, we call it the adjacent side. Okay, so we have our adjacent side or opposite side. Now, since we are on the XY plane, okay, we also call the vertical part of the triangle, we call that the Y coordinate, and here we call this the X coordinate. Okay, so looking at this, when you study in geometry, there was a way to solve for unknown angles. So what I want to do is I want to solve for an unknown angle and figure out what angle this is. And we're going to talk about why this angle is special. Now, this isn't something that necessarily you're going to need to do on your quiz, but I want to show you this relationship. So I'm going to grab an extra piece of paper because I didn't leave enough space here. This is not something I expect you to know how to do right now, but just following along. So remember, if I want to figure out sine of theta, okay, sine is equal to opposite over hypotenuse, or we also call it y over that r variable, okay? So y over r, okay, well, we don't know what r is right now, okay? So we have to solve for r. We know that y is 1/2, so let's solve for our r value. So remember, x squared plus y squared is equal to r squared. So I'm going to have √3 over 2 squared plus 1/2 squared equals r squared. Okay, so squaring √3 over 2, so it's √3 over 2 times √3 over 2 plus 1/2 times 1/2. Okay, so this comes out to 3 over 4, and this comes out to 1 over 4. Okay, so 3/4 plus 1/4 is 1. So the radius of this diagram is 1. Okay, which makes finding the sine value very, very nice. So now when I go to find the sine value, we know that sine of this theta is 1/2 over 1. Well, anything divided by 1 is just itself. So the sine of this theta is just 1/2. Okay, so we have the special triangle. And the reason it's special is because when we create the side lengths of 1/2 and root 3 over 2, the r value, the hypotenuse, will be 1, which makes calculating our sine and cosine values very nice because we're going to divide it by 1. Okay, so let's figure out what this angle is. If this angle is so special that it's creating a radius of 1 or a r value of 1, a hypotenuse of 1, we should probably know what angle it is. So just to review from geometry, solving for an unknown angle, we have to undo this sine. Okay, and undoing, we use the sine inverse function. So we're going to take the sine inverse of both sides. That cancels out to give me theta, sine inverse of 1/2. Now, once again, it's not something you're going to have to know right now. I'm showing you this relationship in this special triangle. Okay, so if I do sine inverse of 1/2, we get 30 degrees. So this angle is 30 degrees. Okay, so it's a very special triangle because it creates that hypotenuse of 1. So we already calculated sine of 30. Okay, we got this 1/2. What would cosine of 30 be? Well, it'd be adjacent over hypotenuse, or x over r, which is root 3 over 2 over 1, which is just root 3 over 2. Okay, all right. Let's talk about this next triangle. Okay, once again, I got to redraw this diagram real quick. Boop. Boop. Oh, look at that perfect triangle. Okay, so here we go. Okay, so let's say this is good practice for us. Okay, let's say this is at a coordinate point, because we talked about coordinate points a lot too, because it's where we rotate to, of root 2 over 2 over root 2 over 2. Okay, so remember, just a review from last week, that means that this is my x coordinate, this is my y coordinate, and we go to label it. The x coordinate is the horizontal aspects of the triangle, so this is root 2 over 2, and y is the vertical, so this is root 2 over 2. Okay, so now I have a triangle where it's root 2 over 2, root 2 over 2, and I have this angle theta. Okay, once again, we can calculate, using sine, we can calculate what angle that is. Okay, so if I go to do sine of this angle, let me pull this paper up. We know sine of theta is equal to opposite over hypotenuse, which is y coordinate over the r value, which in this case, we know that y value is root 2 over 2. Once again, we don't know that r value. Okay, so what we need to do is find the hypotenuse. X squared plus y squared equals r squared. X squared would be root 2 over 2 squared plus root 2 over 2 squared equals r squared. So like root 2 over 2 times root 2 over 2 plus root 2 over 2 times root 2 over 2. Okay. So then when I multiply those, I get 2 over 4 plus 2 over 4. 2/4 plus 2/4 is 4/4, which equals 1. So r squared equals 1. And I didn't do this in the last problem because if you square root 1, you still just get 1. So once again, I have a triangle with these nice side lengths that create a hypotenuse of 1. Okay, which makes finding our sine values very nice because we're dividing by 1. So the sine of this angle would be root 2 over 2, and the cosine of this angle would be root 2 over 2. Okay, now once again, figuring out what this angle is important. If it's creating such a special triangle, it's important to know what angle this is. So once again, we're going to use that sine inverse. Okay, we're going to use that sine inverse function. So we know the sine of this angle is root 2 over 2. So if I sine inverse both sides, the opposite of sine inverse of root 2 over 2, okay, sine inverse, I'll actually use my fraction function here, root 2 over 2 gives me an angle of 45 degrees. So this is a 45-degree angle. Okay. All right, so that means sine of 45 is root 2 over 2, and cosine of is root 2 over 2. Now, why is it that the side lengths are the same? Well, what does that tell us about the angles? Well, we know the angles in a triangle add up to 90 degrees, so if I do they add up to 180 degrees. So if I do 180 degrees minus my right angle, minus that one angle, we know the other angle is also 45 degrees. So this is actually called a 45, 45, 90 triangle. It's a special right triangle that you may or may not have studied in geometry. So that makes sense. If the angles are the same, what does that tell us about the side lengths? The side lengths also have to be the same. Okay, so I have this 45-degree angle that's creating side lengths of root 2 over 2 and root 2 over 2. If I look over at my first triangle, we can use the same math to figure out the other missing side length. Okay, I do 180 minus my right angle minus my 30-degree angle, which leaves us with 60 degrees left over. So that means this top one. So this one's called a 30, 60, 90 triangle. Creates those side lengths of 1/2 and root 3 over 2. Okay, last diagram. Okay, let's say we have this coordinate point up here. Let's label it as, let's say it's 1/2 comma root 3 over 2. Remember, that's your x, that's your y. So the x coordinate goes on the x-axis, the horizontal portion of the triangle, and the y value goes on there. Now, we can see that they're similar side lengths, they're just opposites of each other. So now my vertical length, my y coordinate was 1/2. Now my x coordinate's 1/2. So these are the same triangles, just flipped on their sides. So I can go through and show you the math again of doing x squared plus y squared equals r squared, but it's the same side length. So if we know they're the same side lengths, is the math going to change at all? No. Okay. We still have this angle theta. Okay. Now, if I go to do sine of theta, we know it's opposite over hypotenuse, or y over r, so it's going to be root 3 over 2 here. Okay, well, if I sine inverse that, it should be no surprise that we're going to get an angle that we've already figured out. So if we sine inverse, let's do root 3 over 2, we get a 60-degree angle, which should make sense because it's the same triangle, just flipped on its side. So now instead of the 30-degree angle being what's called our reference angle, our 60-degree angle is now our reference angle. Okay, which means sine of 60 is root 3 over 2, and cosine of 60 is 1/2. Okay, so let me review why I just did this. Okay, first of all, it was nice to review how to find missing side lengths using x squared plus y squared equals r squared, because you're going to need that this week again. It was also nice to review our sine and cosine ratios and knowing that opposite over hypotenuse, or y over r, is our sine value. For cosine, it's adjacent over hypotenuse, or x over r. Okay, just reviewing those ratios was important moving forward. These are triangles that are going to show up a lot as we do calculations over the next couple weeks. They're called our special triangles. Okay, so we know that 30, 60, 90s and 45, 45, 90-degree triangles are nice because they create a hypotenuse of 1. Okay, so that's going to be really important going forward. Now, here's the thing that related back to today's lesson. I have confidence after looking through some of your work that if I tell you to draw a 30-degree angle, most of you can estimate where a 30-degree angle is. Now, as we're making this conversion to radians, knowing what 30 degrees is in radians is very helpful for us moving forward, because then we can have a reference in radians as well as in degrees. Okay, so what I want you to do, okay, is I want you to flip over to the back side, and I want you to take our special degree rotational measurements that we've just studied, 30 degrees, 45 degrees, and 60 degrees, and I want you to use our conversions from the front of your notes to convert these into radians. So go ahead and pause your video and convert these degrees into radians. All right, so just to go over what you came up with, so we take 30, we multiply it by pi, and we divide by 180. Once again, we're going to leave pi in our answer, so really we just care about what fraction is 30 over 180. Okay, so 30 over 180 comes out to be 1/6. So some people write it as 1 pi over 6, but the more standard way to write it is just pi over 6 is the radian measurement. Okay, so pi over 6 is 30 degrees. Okay. 45 degrees, well, we take 45, multiply by pi, and divide by 180. Once again, we care about just leaving our pi, so we're going to figure out what what fraction is 45 over 180, and we end up with 1/4 of a pi, which is written as just pi over 4. Okay, last one, 60 times pi over 180. Once again, we leave pi, we just care about what fraction this is, so we divide that in our calculator, convert it down to a fraction. Okay, we can do it by hand by canceling out the zeros and figuring out how many times 6 goes into 18. Okay, but this turns out to be 1/3 of a pi, which we write as pi over 3. Okay, which should make sense because all radians are, guys, is it's a fraction of a pi. Okay, so as my degrees get larger, my fractions get larger. Okay, what's the smallest degree measurement here? It's 30 degrees. Well, if someone comes up and offers you a slice of cake and you want to take the smallest slice, are you going to take 1/3 of the cake, 1/4 of the cake, or 1/6 of the cake? So as the degrees get smaller, your fractions get smaller, or vice versa. Okay, so these are important radian measurements that we're going to be using moving forward next week. That's important for us. Okay, all right. So let's talk about our new trig ratios. So half of your homework is going to be about converting degrees to radians and knowing that conversion, which I went over on the front of the notes. The other side is going to be calculating our 6 trig ratios. Okay, so we've already talked about 3 of them. And let me redraw this diagram real quick. Okay, so let's say I have side length here, and I rotate, let's just call it theta, and I rotate to here. Okay, remember this is our XY coordinate of where we're located when we rotate certain degrees. Okay, and then I draw my right triangle. And some of you on your quiz, I see you're drawing your triangles, you're drawing them to the y-axis. So I'm gonna draw you 2 examples of what I don't wanna see. I see some people doing this. Okay, that's not okay. And I also saw some people doing this. Okay, well I can't rotate it all from here if that's just a straight line. So here's my rotation. Okay, so we have our X side, our Y side, and our R side. Okay, so what we learned is that sine of theta is equal to opposite over hypotenuse, okay, which is our y coordinate over our r. Now, I want to talk about r a little bit really quickly because we kind of arbitrarily started calling that r, okay? But the reason we call it r is because we're going to start talking about not only rotational measurements, that's our degrees, but we're going to talk about, that's a really poorly drawn circle, but we're going to talk about how far around a certain circle have we traveled. Okay, well, that's our radian measurement. So figuring out what this value is right here, okay, that's our radian measurement, which is dependent on the radius of the circle. So remember, radius is the distance from the middle to the outside of the circle. Okay, so that's why we call this r, because it's the radius of the circle is always going to be the hypotenuse. Okay, the radius of the circle is always going to be the hypotenuse of your diagram. Okay, equals the hypotenuse of your diagram. So that's why we call that r. Okay, so cosine, back to our ratios, is adjacent over hypotenuse, which is x over r. And then our tangent theta is equal to opposite over adjacent, which is y over r, or y over x. Okay, so those are the 3 that we worked on last week. Okay, now it's really important, and I'm going to draw this little diagram here, is that we understand in which quadrants is our y's positive, our x's positive, or our x's are negative, or our y's are negative, because we kept on messing that up. Okay, so if I go here, this is 3rd quadrant, this is 4th quadrant. So in the 1st quadrant, if we think about a point located anywhere in this circle, okay, let's just draw a circle right here. Okay, if I draw a point anywhere in this circle, what's going to be true about my x's and y's? Well, in the 1st quadrant, our x's are positive and our y's will always be positive. Okay, so if you draw a diagram in your 1st quadrant, your y's will always be positive and your x's will be positive. As I switch here to this side, quadrant 2, okay, which one of my coordinates changes, okay? Remember, this is our origin. This is 0, 0 right here. So as I go to this side of the origin, which one of my values changes? Does the x change or does the y change? Okay, well, our x's are negative and our y's stay positive in this quadrant. Okay, down here in quadrant 3, our x's will always be negative and our y's will always be negative. And then quadrant 4, our x's now turn positive again because we're on this side of the x-axis, and our y's become negative. So it's important to know, depending on where you are, and a lot of us were missing homework questions because it's depending where I'm at, my x's might be negative or my y's might be negative, and that's important to know. All right, so now moving on, we're going to talk about our reciprocal trig functions. Okay, remember reciprocal is just a fancy math word for meaning flipped. Okay, so we're going to have 3 new ones, but all they are is they're flipped versions of sine, cosine, and tangent. Okay, so the first one we're going to talk about is called cosecant. Okay, cosecant. Okay, it's written as CSC of theta, and it is the reciprocal of sine. Okay, and we write that as 1 over sine of theta. That means it's reciprocal. Okay, now I'm not going to do this math. Instead, we're just going to reciprocal sine. So that means it's going to be hypotenuse over opposite, and y over r would be its calculation. Okay, so a lot of people, what they want to do is they see cosecant and they think it goes with cosine. Okay, cosecant is buddies with sine, so I'm going to call it sine's buddy. Okay, the other one that we're going to learn about is called secant. SEC is its abbreviation, and this is the reciprocal of cosine of theta. Okay, well, what's the flip of cosine? I come up here and flip this, so it's going to be hypotenuse over adjacent. I wrote this wrong. This would be r over y, and this would be r over x. Okay, last one. Screw this up a little bit. Okay, and this is whose buddy? Well, secant, we want to pair that with sine because they both start with s's, but this is actually cosine's buddy. So we need to know that those go together. The last one is the easy one to remember because it's cotangent, and this is COT, and this is 1 over tangent of theta. And what's the reciprocal of tangent? Well, instead of opposite over adjacent, it'd be adjacent over opposite, which would be x over y. And this is tangent's buddy. So usually what we end up doing is we end up finding our sine, cosine, and tangents and then taking the reciprocals afterwards. Okay, so let's look at an example here. All right, so we want to find all 6 trig ratios, but they give you one of them. So sine of theta is 3/7. So I come up here to the sine and make sure I remember what sine is. Sine tells me the y coordinate and the r value. So my y value is 3 and my r value is 7, but we're in quadrant 2. So once again, that's important to know. How does that affect what my x value is going to be? So if I draw a diagram in quadrant 2, okay, we're at 3 is my y value. So we know that this is 3, and we know my r value, which now stands for the radius, or the hypotenuse of the same thing, is 7. What we don't know is we don't know our x value, but based on our diagram, if we're on this side of the x-axis, we know that it's going to be a negative value. Okay, so let's calculate it. X squared plus y squared equals r squared. X squared plus y squared equals r squared. So x squared plus 9 equals 21. Oh, not 21, 49. Okay, so then I subtract 9 from both sides, and I get x squared equals 40. And then I get that by square rooting, x is the square root of 40. So that's our calculation, but we already said that since we're over here, it's going to be a negative square root of 40. Okay, so now we have all our sides. We have our x coordinate, we have our y coordinate, we have our r, so now we can find all of our ratios. So cosine would be x over r, so it's going to be negative root 40 over the r, which is 7. Make sure that negative is there. And that's why a lot of you were getting errors on some of your homework problems and you felt like you were doing it right, but you didn't make your x coordinate negative. Tangent is y over x, so my y coordinate is 3 over my x coordinate is negative root 40. Okay, so now we start to get into our reciprocal functions. Okay, so cosecant, that's the one you want to pair it with cosine, but it's not, it's sine's buddy. Okay, well, if I already know what sine is 3/7, well, what's the reciprocal of 3/7? 7/3. It's just the reciprocal of sine. Secant, that's cosine's buddy. Well, we already found cosine was negative root 40 over 7, so we flip it. We get 7 over negative root 40. Last one, cotangent. We know cotangent is the reciprocal of tangent. We found our tangent ratio already, so we flip it, and we get negative root 40 over 3. And those are my answers. All right, so this is really important for your homework this week, being able to do problems like this. Okay, so following along with this problem is really important. Make sure you pay attention to what it gives you. It might give you cosine, it might give you tangent, which is going to change what you're given, whether you're given the y coordinate, the x coordinate, or the hypotenuse. Okay, so make sure you pay attention to that. Make sure you pay attention to what quadrant you're in, because that's going to determine whether your y's are positive or negative, or your x's are positive and negative. Okay, and then just make sure that you answer in fractional form, and you can use that fraction button on WAMAP to put your answers there. Okay, so this is really important for your homework. And then if you flip over the front side of your notes, just your conversions is a big part of your homework. Okay, so make sure you know how to do those two things as you practice. Make sure you watch the notes and do your WAMAP practice problems prior to showing up to your Zoom classroom, or at least attempt to, so that we can go over misconceptions and answer questions as we have them. Okay. I look forward to see you guys on Tuesday and Wednesday. Hope you guys are doing well. See you soon.